Welcome to the deep dive. For, gosh, 2 decades now, PCI Express, PCIe, it's been this quiet workhorse, hasn't it?
Absolutely, just humming along in the background.
Yeah, reliably doubling data rates, almost like clockwork. Predictable, powerful stuff fueling, well, everything.
Mm-hmm.
But what we're getting into today, it's not just another speed bump. We're talking PCIe 6.0.
And it's a big one.
People are calling it the most profound architectural upheaval in its history. Seriously, we're talking 64 gigatransfers per second per lane.
Which is just staggering. For a by-16 link, that works out to 256 gigabytes per second bidirectionally.
Mind-boggling speeds. But you know what's really striking isn't just the number, it's why they had to change things so dramatically.
Exactly. This wasn't just, let's make it faster. It was, as the spec folks put it, a matter of necessity.
A necessity. Driven by what?
Driven by the basic physics of it. The physical limitations of copper interconnects at extreme data rates. The old way, well, it just hit a wall.
Okay, a matter of necessity, hitting a wall. That sounds serious. Unpack that for us. What wall, and how did they possibly get around it?
Right. So to get past these fundamental limits, PCIe 6.0 really relies on what you could call the new triad. 3 core technologies working together.
A triad. Okay, what are they?
First, there's 4-level pulse amplitude modulation. You'll hear it called PAM4 signaling. Second, a totally new way to package data called flow control unit, or a FLT-based encoding.
Okay, PAM4 FLTs, and the third.
And the third, absolutely crucial, is forward error correction, or FEC. These 3 really work hand in glove.
PAM4 FLTs, FEC. Got it. So our mission today is basically to give you the shortcut.
Exactly. Help you understand this revolutionary triad, why it was needed, like really needed.
And what it actually means if you're designing or validating or deploying these PCI 6.0 systems. We're hoping to share some maybe surprising facts and definitely essential insights.
That's good.
So let's dig into that why first. Hitting the frequency wall, as they call it. The goal, obviously, double the speed from PCIe 5.0's 32 GTs.
Up to a crazy 64 GTs per lane.
But the old signaling method, NRZ, non-return to zero.
Yeah, the simple 2 voltage levels, 1 for 0, 1 for 1, been around forever.
If they'd stuck with that, what would have happened?
With a basic signaling frequency, the rate things wiggle on the wire,
Right.
but it had to double too. From 16 gigahertz, which was already pushing for PCI 5,
Up to 32 gigahertz.
32 gigahertz, and that's where you hit the wall hard. At that frequency, your standard FR4 PCB material, the green stuff circuit boards are made of, it just eats the signal.
Eats it.
Yeah, the insertion loss, the signal attenuation, it goes through the roof. We're talking maybe over 60 gigaorders of loss. Your signal is just gone.
So transmitting reliably becomes physically impossible for, like, normal computer systems.
Completely impossible for mainstream stuff. It was a dead end. No way forward with NRZ at that speed.
Okay, so NRZ is out. What's the brilliant solution?
The solution they landed on is PAM4, 4-level pulse amplitude modulation. It wasn't brand new. It was already working well in high-speed networking, like Ethernet.
And how does PM4 work? How does it dodge that frequency bullet?
It's clever. Instead of just 2 voltage levels for 1 bit, PAM4 uses 4 distinct voltage levels.
New levels, okay.
And those 4 levels let you encode 2 bits of data, zeros, 0, 1, 10, or 11, in the exact same slice of time, the same unit interval that NRZ used for just 1 bit.
Ah, so you're packing twice the information into the same time slot.
Precisely. It's a masterstroke, really. It lets PCIe 6.0 hit that 64 GT's data rate. But the simple rate, the rate the voltage levels actually change, is only 32 gigabaud.
Which means?
Which means the fundamental Nyquist frequency stays at 16 gigahertz, the same as PCIe 5.0.
Wow. Okay, that's the magic. That's huge.
It's absolutely critical because it means designers can, for the most part, stick with existing PCB materials, existing connectors, maybe with some tweaks. It preserves the channel reach, the distance the signal can travel reliably. That's vital for adoption, for cost.
Okay, but there's always a catch, isn't there?
Yeah.
This electrical efficiency, squeezing 4 levels in, it must come at a price.
Oh, it definitely does. The price is paid in signal integrity. A significant cost, as the documents say.
How so?
Think about it. You're cramming 4 voltage levels into the same total voltage swing that used to hold just 2. When you look at the signal on an oscilloscope, you see these eye diagrams.
Right, the open space where the receiver can read the signal clearly.
Exactly. With NRZ, you have one big open eye. With PM4, because you have 4 levels, you get 3 smaller eyes stacked vertically.
3 smaller eyes.
And each of those eyes is roughly only 1/3 the height of the old NRZ eye.
Ah, much smaller target to hit.
Much smaller. Which means the signal is inherently much weaker relative to any noise, We measure this as signal-to-noise ratio, SNR, and PM4 causes a severe SNR hit around 9.5 dBs worse.
9.5 dBs, that's a lot.
It is. It means the PM4 signal is dramatically more susceptible to noise, jitter, crosstalk, you name it. Any little imperfection in the channel gets amplified, basically.
Wow. Okay, so let's recap that quickly for you. PCIe 4.0, 16 GTs, 5.0 doubled it, 32 GTs, both using NRZ. Then 6.0 doubles again to 64 GTs, but has to switch to PM4.
Had to, no choice.
And the genius is keeping that Nyquist frequency at 16 gigahertz, same as Gen 5. But the trade-off is this much more fragile signal. And I remember seeing the channel loss budget actually tighten too, right? From 36 dB down to 32 dB.
That's right. Less margin for error overall, even before you consider the PM4 sensitivity. It really underscores the challenge.
So if the signal itself is so fragile, so prone to errors, how on earth do you guarantee reliability? PCIe is known for being rock solid. It sounds like you can't just, prevent errors anymore.
You can't. And that's the core philosophical shift in PCIe 6.0. The old requirement, that super strict raw bit error rate of 10 to the minus 12.
One error in a trillion bits.
Yeah, that became physically and economically just impractical with PM4 at these speeds. So PCIe 6.0 makes a philosophical departure.
From what to what?
From error avoidance, trying to make the signal perfect, to an error management strategy.
Error management, okay. Like accepting errors will happen, but having a plan to deal with them?
Exactly like that. It's like building a really, really good cleanup crew instead of trying to keep the factory floor perfectly sterile 24/7.
Okay, so the standard actually allows a higher raw error rate and then relies on mechanisms downstream to fix it. That feels risky.
It sounds it, but it's a calculated risk with very robust mitigation. The spec now accepts a raw error rate, the first bit error rate, or FBER, of 10 to the minus 6.
1 in a million. That's a million times worse than 1012.
It is, but remember, that's the raw rate before the cleanup crew gets to work. It's a design parameter for this multi-layered reliability system. It's not the final error rate the user sees.
Okay. So what's the first layer of that cleanup crew?
That's forward error correction, FEC. It's mandatory in Gen 6. It's a lightweight mechanism, adds just a little bit of redundant data, 6 bytes of error-correcting code, ECC, to each packet.
And what does that ECC do?
It lets the receiver detect and crucially correct single-byte errors on the fly, without needing to ask for the data again, without a retransmission.
So it fixes small glitches instantly. And is it fast? Latency is key for PCIe.
Extremely fast. Very low latency. It adds less than 2 nanoseconds to the link latency. It's designed to be almost invisible from a timing perspective.
Okay, so FEC handles the small stuff. What else is in this error management toolkit?
Well, FEC works best when it operates on predictable, fixed-size chunks of data.
Makes sense.
And that requirement was the direct impetus for adopting the second pillar, FLIT mode, flow control unit mode.
FLIT mode, how does that work?
Everything on the link, all the data packets, the control messages, everything gets chopped up and packaged into fixed-size 256-byte containers called FLITs.
Everything's a standard-size box now.
Exactly. And this brought some nice side benefits, too. It got rid of the old 128B, 130B encoding overhead from Gen 4 and Gen 5.
Right, where you had 2 overhead bits for every 128 data bits.
Yeah. FLIT mode achieves almost perfect 1B1B encoding. Basically, every bit on the wire is useful data, much more efficient. Plus, it simplified the controller logic and actually helped reduce latency in some ways, too.
Okay, so PM4 makes errors more likely, FEC fixes the small ones, and LETs package everything neatly for FEC. Is there a final safety net? What if FEC can't fix an error?
There is. That's the third piece. A strong cyclic redundancy check, or CRC. There's a 64-bit CRC embedded inside each FLIT.
Right, a checksum.
Yep. So after the FEC logic does its best to correct any errors it finds, the receiver then calculates the CRC on the FLIT data.
And if the CRC check fails?
That means an uncorrectable error happened, something FEC couldn't handle. When that happens, the standard link-level retry mechanism kicks in. The receiver sends a nag, basically saying, hey, that last FLIT was bad, send it again.
The traditional retry, so that's still there as the ultimate backstop.
It is. And this combination, the FEC fixing most errors, plus the strong CRC catching anything FEC missed and triggering a retry, is incredibly robust. Even with that raw error rate of 10.6, the chance of a FEC actually needing a replay is very low, also around 10.6. And the final rate of undetected errors, the ones that slip through everything, it's negligible. Way, way better than the required reliability targets. So you still get that rock-solid, low-latency PCIe performance, just achieved in a different way.
Error management, not just avoidance. That makes sense. So we've fundamentally changed how the signal works, how errors are handled. What does this mean for the engineers actually building and testing PCIe 6.0 stuff? I assume the old test gear isn't going to cut it.
Not even close. This triad PM4 FEC FEL-FI LTs means your Gen 5 test equipment is basically obsolete for validating Gen 6. You need a whole new class of instruments.
Yeah.
Higher performance, much more sophisticated analysis software, and honestly, a lot more automation because it's so complex.
Okay, let's talk tools. Start with the oscilloscope, the eyes of the physical layer. What's needed there?
To even see these PM4 signals accurately, you need serious bandwidth. Minimum 50 gigahertz analog bandwidth on the scope. And super high sampling rates, like 256 gigasamples per second or more. These signals are incredibly fast.
And remember those tiny PM4 eyes?
Exactly. Because the eyes are so small and the signal is noisy, the scope's own noise floor becomes critical. You need a very low noise front end. Plus, really advanced software.
Software for what, specifically?
Well, you need specialized PMN analysis software. It's mandatory now. It does things like build the PM4 eye diagrams correctly, perform incredibly complex jitter analysis, breaking down timing variations across all 12 different edge transitions in PM4.
12 transitions, wow.
Yeah, it gets complicated fast. And it calculates these new compliance metrics we'll talk about, like SNDR and RLM. The software also has to be smart enough to mathematically remove the effects of the test fixtures and probes, that's called de-embedding, and apply a reference receiver model to see the signal as the actual chip would see it.
Okay, so scopes need a major upgrade. What about bit-error ratio testers, the BERTs? They stress the receiver.
Right. Their main job is generating those 64 gigabaud PM4 patterns and then detecting errors coming back from the device under test.
Yeah.
But for receiver testing, it's more than just sending a clean signal.
Need to send a bad signal.
Precisely. The BERT has to create a stressed eye. It deliberately injects very precise, calibrated amounts of garbage into the signal, different types of jitter, noise, interference, to simulate real-world conditions and see how well the receiver handles it.
And what's new for BERTs in Gen 6?
The absolute game changer is that the error detector part of the BERT must be FEC aware.
FEC aware, meaning it understands the forward error correction.
Exactly. It can't just count raw bit errors anymore. It needs to look at the incoming data stream, understand the FEC structure, and identify FEC symbol errors. And critically, it needs to distinguish between errors that the FEC could correct and errors that are uncorrectable.
So it can tell you not just if there are errors, but how well the FEC is coping with them.
Precisely. That capability is essential for properly stress testing the whole FEC mechanism. And just setting up that stressed eye correctly is so complex, automated test software is basically mandatory now. It coordinates the BERT and the scope, tweaking all the impairments, running the tests. It's too much to do manually.
Makes sense. Okay, moving up the stack. Protocol analyzers and exercisers. These look at the logical layer, the actual data packets. What's the big change there?
FLIT mode decoding. That's the absolute baseline. The analyzer software has to understand the new 256-byte FLIT structure, capture it, decode it, and display it intelligently, showing you the TLPs and DLLPs hidden inside those FLITs.
So it needs to speak the new language of FLITs.
And beyond just decoding, a good Gen 6 analyzer needs to be smarter about errors. It should be able to spot errors at multiple layers, physical layer, things like FEC symbol errors or CRC failures within a FLIT.
Things you couldn't even see at the protocol level before.
Exactly. They were invisible before. But the real power comes from correlating those physical errors with what happens at the protocol level. Like seeing a burst of FEC errors immediately followed by a link-level retry, an EC, or seeing specific errors that cause the link training state machine, the LTSSM, to go haywire.
And the exerciser part.
That lets you pretend to be the other end of the link, like the CPU or an endpoint device. You can generate specific traffic, inject protocol errors on purpose, mess with the link training invaluable for debugging tricky interaction issues and ensuring compliance.
And I guess just plugging the analyzer in is harder now, too.
Oh, yeah. At 64 GTs, the physical probe or interposer you use to tap into the link is a huge signal integrity challenge itself. They have to be incredibly high fidelity, low loss, almost electrically transparent so they don't disturb the link they're trying to measure.
It sounds like the lines between physical layer testing and protocol testing are really blurring.
They absolutely are. That's why tools that enable cross-layer analysis are becoming so important.
Yeah.
We mentioned Teledyne LaCroix's CrossSync PHY earlier, that ability to link a scope waveform directly to a protocol trace.
Trigger the scope on a specific protocol event, like a NA.
And instantly see the exact electrical glitch that caused it. That speeds up root cause analysis like nothing else. It takes the guesswork out.
Okay, so new tools, new capabilities. This also means a whole new language of measurement, doesn't it? Especially when looking at that PM4I diagram.
Definitely. Mastering PM4I analysis is key. That diagram with 3 stacked eyes is just way more complex than the old single NRZ eye. You can't just slap a simple pass-fail mask on it anymore.
What kind of complexities do you see?
Well, for one, asymmetry is common. The 3 eyes are rarely perfectly identical. Usually the middle eye is a bit wider, maybe taller. And then you have to worry about linearity. Are the 4 voltage levels evenly spaced? And skew, do all 12 possible transitions happen at the right time relative to each other? Any deviation there is a prime source of errors.
So because it's so complex, there are new ways to quantify the quality, new metrics.
Yes, PCIe 6.0 introduced new mandatory transmitter quality metrics. Probably the most critical one is SNDR, signal-to-noise and distortion ratio.
SNDR, what does that tell you?
It's like a single number that gives you a holistic grade for the signal quality. It measures the power of the clean, ideal signal compared to everything else: noise, jitter, distortion, nonlinearity, all the junk.
And what's a good SNDR value?
For PCIe 6.0 compliance, you need an SNDR above 32.5 dBp. Higher is better, means a cleaner signal.
Okay, SNDR is the overall grade. What else?
There's RLM ratio of level mismatch. This one specifically looks at that vertical spacing of the 4 PM4 levels. Are they evenly distributed?
The linearity thing.
Exactly. An ideal RLM is 1, meaning perfect spacing. Its compliance limit is 0.9. If it's lower, your levels are squished or stretched unevenly, which makes the receiver's job harder.
And jitter, measuring timing variation.
Oh, jitter measurement becomes way more complex. With NRZ, you mainly looked at 2 transitions. With PM4's 4 levels, you have 12 different types of transitions between levels.
12 ways the signal can change state.
Right. So just measuring 1 or 2 isn't enough. Compliance requires analyzing the timing distributions of 48 different edges across those 12 transitions to properly separate out the random jitter, the deterministic jitter, and get the total jitter.
It really sounds like it. Okay, let's shift to BER testing bit error rate. We talked about that philosophical shift, accepting a higher raw error rate, the 10.6 FBER. How does that change testing?
Well, you have to understand the difference between pre-FEC BER and post-FEC ER.
Okay, pre-ECER.
That's the raw error rate before the forward error correction does its magic. It tells you about the fundamental quality of the signal coming off the wire and through the receiver's initial cleanup. It's equalization. It basically answers, is the signal good enough for FEC to even have a chance?
Right. It's the input to the FEC decoder.
Exactly. And remember that 10.6 is the target for that pre-FEC BER. It's not a pass-fail like the old 10.12 used to be.
Got it. So what's post-FEC BER?
That's the bottom line. It's the error rate after FEC has corrected errors and after any necessary retries triggered by CRC failures.
Right.
This is the final error rate that the application layer sees.
And that needs to be?
Effectively 0. Or at least meet those extremely high PCIe reliability targets, like FIT rates much less than 1. Post-FEC BR answers the big question. Is the whole system channel, receiver, FEC, CRC, retry working together correctly to deliver reliable data?
Okay, pre-FEC tells you if the signal is okay. Post-FEC tells you if the final result is okay. Is there anything else?
Yes, and this is perhaps the most insightful metric for understanding link health in real time. The FEC symbol error rate, or SEER.
How does that work?
A FEC-aware BERT, or even the device itself, can monitor the FEC decoder's activity. Specifically, it can count how many FEC symbols are being corrected.
Not just errors, but corrected errors.
Right. This gives you a super high-resolution, real-time window into the link's margin, a low, steady rate of corrected symbols. That's normal. That's FEC doing its job on the noisy PM4 signal.
But if that rate starts to climb?
If that corrected symbol count starts increasing rapidly, even if the post-FEC BER is still 0, that's your sensitive early warning. It tells you the raw signal quality is degrading, the link is losing margin, and you're getting closer to that FEC cliff where uncorrectable errors start happening. It turns FEC from just a correction mechanism into a powerful diagnostic tool.
Like a canary in the coal mine for signal integrity.
Exactly like that. Very sensitive.
One more measurement technique, lane margining. That's been around, but how does it adapt to PAM4?
Lane margining is that cool feature where system software can tell a receiver, hey, try shifting your sampling point a little bit left or right in time or up or down in voltage, and tell me if you still get good data.
It maps out the edges of the eye while the link is live.
Right. In the PM4 world, since you have those 3 eyes stacked vertically, the margining commands now apply to all 3 eyes simultaneously. There are new registers to report PM4-specific margining capabilities, like how many timing or voltage steps it supports.
And why is this so useful?
It's a critical tool for system validation, especially in big data centers. You can non-disruptively check the health of thousands of links in running systems, identify any links that have low margin, maybe due to aging or temperature changes, and compare that real-world performance back to your lab measurements. It bridges that gap between design validation and actual field reliability.
Okay, so we have these complex signals, new ways to measure them, powerful tools, but things still go wrong. How do you debug failures, especially signal integrity issues, when the margins are so tight?
Yeah, that tighter 32 dB loss budget for Gen 6 leaves significantly less margin for imperfections. PM4's sensitivity just amplifies any channel flaw.
What are the usual suspects when a link fails due to signal integrity?
The big three are still insertion loss, crosstalk, and reflections. Insertion loss is just too much signal attenuation. You diagnose it with a VNA or TDR. The fix is usually better PCB materials, ultra-low loss stuff, shorter traces, fewer connectors.
Okay, crosstalk.
Noise bleeding over from neighboring lanes. Much bigger problem with PM4's smaller vertical eye opening. Again, a VNA helps characterize it. Mitigation is all about careful layout. More space between signal pairs, maybe using strip line routing, better connector design.
And reflections.
That's intersymbol interference, ISI, caused by impedance mismatches. Little bumps in the road where the signal bounces back. A TDR is the main tool here. Debugging means meticulous attention to maintaining that constant 85 ohm differential impedance everywhere. Things like backdrilling vias, optimizing connector footprints. It's painstaking work.
And beyond fixing the physical channel, what advanced techniques help?
Simulation is huge. Pre-silicon channel simulation using good IBIS-AMI models for the transmitter and receiver is no longer optional. It is essential.
Why essential?
It lets you predict the eye opening, test out different equalization settings, run what-if scenarios before you build hardware, saves immense time and cost. And then, as we discussed, that cross-layer analysis is the most powerful debugging methodology.
Connecting the dots between the physical glitch and the protocol error.
Exactly. Seeing that burst of crosstalk on the scope, right when the protocol analyzer flags a CRC error and an NAC, that tells you exactly where to look. It cuts debug time from days or weeks down to hours, potentially.
And you mentioned leveraging FEC itself for diagnostics.
Absolutely. Those FEC error counters are like built-in probes giving you that highly sensitive, real-time view into the health and margin.
Remind us how to interpret those counters.
Okay, the correctable FEC errors counter goes up when FEC fixes a symbol. A low, steady rate, totally normal. But if it suddenly spikes or trends upwards over time, that's your early warning. Raw signal quality is dropping, margin is shrinking.
And the uncorrectable FEC errors.
That increments when FEC encounters an error it can't fix. These should always be caught by the CRC check downstream, triggering a retry. If you see a lot of these, you've got serious signal integrity problems, or maybe even a bug in the FEC decoder logic itself.
So you can stress test this, see where the breaking point is.
Yes, that's key for robustness testing. You use a bird to inject errors, often specific patterns like burst errors, and you watch those FEC counters. You're trying to find the FEC cliff, the exact error rate or burst length where the uncorrectable errors suddenly shoot up and your link performance tanks. Knowing where that cliff is tells you how much margin you truly have.
Okay, one more debug area. Link training failures. When the link just won't come up properly. LTSSM issues.
Yes, the LTSSM.
Yeah.
Debugging that is almost exclusively the domain of the protocol analyzer. You need to capture and decode those training sequences, TS0, TS1, TS2, to see the handshake step by step.
What are common failure points?
You might see the link get stuck early on, failing to achieve symbol lock in it. Maybe one side isn't sending valid patterns, or it gets stuck in one of the equalization phases, maybe looping endlessly trying to negotiate settings. That often points to a logic bug in how one side implemented the state machine.
Any new wrinkles with Gen 6?
Yeah, new features like the L0P low power state, where the link dynamically changes width, can introduce new potential deadlocks if not implemented carefully. For example, if both sides try to initiate a width change at the exact same time and wait for the other to acknowledge first.
And if you can't get an external analyzer hooked up?
That's where on-chip debug features become vital. Things like internal LTSSM state registers accessible via JTAG, or maybe some rudimentary internal eye monitoring capabilities can give you those crucial first clues about where things are going wrong.
Okay, shifting gears slightly to system architecture. You mentioned the reach issue with Gen 6. That tight loss budget means passive copper traces can only be what, a few inches long?
Yeah, just a few inches, realistically,
Mm.
which is obviously a non-starter for building, say, large AI servers with accelerators cards far from the CPU or complex modular systems.
So how do you bridge that distance? This is where retimers come in, right? What exactly is a retimer?
A retimer is really the unsung hero of high-speed links, like PCIe 6.0. Think of it as a smart repeater. It's a dedicated chip, a mixed signal IC. There's basically two complete PCIe physical layers, PHYs, connected back to back.
Two PHYs in one chip. How does that help?
It sits in the middle of a long channel. It receives the weak, messy, degraded signal coming in one side. Its internal receiver uses sophisticated equalization to clean up the signal and open the PM4I. Then, crucially, it performs full clock and data recovery, or CDR.
CDR.
It extracts the clean digital data, but also generates a brand new, clean, low jitter clock signal based on the incoming data. Then, using that clean data and clean clock, its internal transmitter sends out a completely fresh, regenerated, full-strength copy of the PCIe signal down the next segment of the channel.
So it doesn't just boost the signal, it completely rebuilds it.
Exactly, it regenerates it. And by doing that, it effectively splits one long, non-compliant, lossy channel into two shorter, independent, compliant segments. It resets the jitter, insertion loss, and lane-to-lane skew budgets.
Resets the budgets, that's the key.
That's the magic. It allows you to chain segments together. The PCIe spec actually allows up to two retimers in series on a single logical link, enabling much longer physical distances and more complex system topologies that would be impossible otherwise.
Okay, so retimers are critical. But we also hear about redrivers sometimes. They sound similar. What's the difference, and why is it so important for Gen 6?
Great question, because it's a critical design choice. A redriver is a much simpler, cheaper device. It's basically an analog amplifier with some simple linear equalization, usually just CTLE.
Just boosts the signal and maybe tweaks the frequency response a bit.
Right. But crucially, a redriver is not protocol aware. It doesn't understand PCIe. It blindly amplifies everything, the signal, the noise, the jitter. It can't fix accumulated timing errors. It can't compensate for lane-to-lane skew. It just makes the whole mess louder. As the saying goes, a redriver cannot fix a broken signal. It might help slightly on a marginal link, but it won't save a bad one.
Okay, so redrivers are simpler boosters and retimers.
Retimers are far more sophisticated and, frankly, essential for PCIe 6.0. They perform that full signal regeneration using CDR. They are protocol aware. They actually participate in the link training, the LTSSM.
They talk PCIe.
They talk PCIe. They eliminate all the accumulated jitter because they retime the data to a new clean clock.
Yeah.
They effectively eliminate crosstalkie once the data is sampled internally. They compensate for and reset lane-to-lane skew. They use advanced adaptive equalization, not just fixed boosts. And they usually have extensive built-in diagnostics like internal eye monitors.
So night and day difference in capability.
Absolutely. For the demands of 64GT's PM4 signaling, with its tiny margins, the retimer's ability to fully reset the signal integrity budgets and intelligently manage the link is non-negotiable for almost any real-world system design. Redrivers just don't cut it at these speeds.
Okay, retimers solve the reach problem, essential for Gen 6. But putting these complex chips into a system must have implications, right? What are the trade-offs for designers?
There are definitely considerations. Latency is probably the biggest one. That whole process, receive, equalize, buffer, CDR, retransmit, it takes time. Each retimer adds several nanoseconds of delay to the link.
Which might matter for latency-sensitive stuff.
Exactly.
Yeah.
For applications like high-performance computing or financial trading, those extra nanoseconds add up and have to be factored into the system performance budget.
What else?
Power and heat. Retimers are complex chips doing a lot of high-speed work. They can be significant consumers of power. A single by 16 PCIe 6.0 retimer might dissipate several watts.
Wow, that's like a small CPU.
Getting up there. So you need careful thermal design, good airflow, maybe heat sinks, and you need to provide them with clean, stable power through a well-designed power delivery network, or PDN. Noise on the power rail can definitely impact their performance.
Any other system-level gotchas?
The new L0P power state is one to watch. That's the feature allowing the link to dynamically shrink its width, like going from by 16 down to by 4 or by 1, without retraining to save power during idle periods.
Seems like a good thing.
It is, for efficiency. But system designers need to make sure the retimers they choose fully support L0P, and crucially, that they've been validated to enter and exit L0P reliably and operate stably in those reduced width states. Bugs in LZO key handling in the retimer can lead to link instability or prevent the system from achieving the expected power savings. It adds another layer to validation.
Okay, so wrapping this all up, reflecting on this deep dive into PCI 6.0, what are the big takeaways for you?
Well, a few key things stand out. First, that fundamental philosophy shift. From desperately trying to avoid errors to actively managing them with that robust FEC plus CRC system, that's huge.
Right. Error management over error avoidance.
Second, the lines are blurring. The convergence of physical and protocol layers is undeniable. Debugging these complex systems now absolutely requires integrated tools and cross-domain thinking. You can't live solely in the analog world or the digital world anymore.
You need to span both.
You really do. Third, PMM4 forced us to invent a new language of measurement. New metrics like SNDR and RLM are essential now, and learning how to use those FEC counters as a real-time diagnostic tool is incredibly powerful.
Using FEC as a sensor.
Exactly. And finally, the retimer.
Yeah.
It's gone from being a niche product for corner cases to a core architectural component. For 64 GT's links in any kind of complex system, retimers are simply essential now, no longer optional.
That really paints a picture of profound change. It feels like the sheer difficulty, the physics pushing back, forced this whole new approach.
It absolutely did. These profound changes in PCIe 6.0, driven by hitting those hard physical limits, have forced a level of collaboration we haven't seen before. Signal integrity folks, protocol experts, system architects, they have to work together intimately now. You can't design in silos anymore.
Which leads to maybe a final provocative thought for you, our listener. As data rates keep climbing, not just in PCIe, but everywhere, think about how this interdisciplinary imperative we're seeing in hardware design might ripple outwards.
Yeah, will we see more fields where the sheer complexity of the problem forces engineers to break down traditional domain boundaries and collaborate in fundamentally new ways? Is this the future of tackling really hard engineering challenges?
Something to definitely mull over. It's been a fascinating dive into the revolution that is PCIe 6.0.
Absolutely. A lot to digest, but truly transformative technology.